me introduce you today. So Tomás Corrêa is a PhD student at the University of Alcalá de Henares in Spain, so very close to Madrid. Actually, it's considered as one of the universities of Madrid. And Tomás has been working on the control of these devices called Modular Multilevel Converters, which are basically devices that allow to generate AC current from DC power sources. And these are, I would say, more and more common, and we will hear about it from Tomás. So Tomás developed this PhD thesis along the last 4 years, basically, and is now just about to defend. So what you will see is a wrap-up of the work and his contributions. And the connection with me has been basically because although the topic and the application is with power electronics, so let's say, the fact is that the core of the, I would say, the contributions, maybe about 2/3 of them, are on communication. And so we dealt essentially with communications, and I was engaged. It was a collaboration we did, and I was engaged in that. Happily engaged, because it was a very interesting and challenging work, so thank you very much. And just tell you that before that, why this came up, because Tomás worked for maybe 5, 6 years at AVL.
At AVL 3.5 years,
okay,
and as development engineer like 7 or 8 years.
Okay, so Tomás had already experience before in power electronics, so he was already into this field, into this domain, and he knew exactly what he wanted to do. So it was a relatively easy thing to find how to contribute to this scope, right? Okay, so thank you for coming, and I pass on the token to Tomás.
Okay, well, thank you very much, Luis, for introducing me. Thank you, everybody, for coming and attending this seminar. Luis explained already a lot of what I had to say at the first slide. What is probably different from the seminars you receive here in-house is that I'm combining two fields of knowledge around electrical engineering, power electronics, and digital communications. So I hope you find it interesting. This is the content of my work. First, I will make an introduction, explain you a bit about what are the modular multilevel converters, the working principles, so you can have at least an idea of the challenges. Explain why the use of digital communication is interesting in this application domain, and highlight some aspects of what I call here network-controlled MMC. So when the MMC is controlled using a network. Then I go to the contributions of the work, starting with 2 protocols that we propose that have as background network and control codesign. I will discuss it a bit better when I come to it. Then I have our quest for reducing the latency to the minimum, because what's very interesting in these applications is that the control cycles are very short, around maximum 200 microseconds, and we have several nodes, hundreds of nodes, and this is probably the most challenging thing. Although I try to reduce latency, it's not always possible to reduce it as much as necessary, so I propose a model-based compensation scheme to improve the control performance. Lastly, I investigate a bit the co-simulation of the system, and we propose a different way of running the co-simulation to make it faster and simpler. And lastly, we go to the conclusions. Well, the modular multilevel converter, here's a picture of a converter by Siemens. It's a link of high voltage direct current transmission between Spain and France. The picture for me is very nice because it gives us an idea of the dimension of those systems. They are really huge, size of a building, not only a converter that it's a cabinet or that you can carry. It's really impressive, in my opinion. This is the circuit diagram. Just a question, how many of you have an electrical engineering background? I guess maybe the the people from computer science is a bit less clear, but the modular multilevel converter, as the name implies, is made of modules. So the boxes here, I call them cells, and we have the cells stacked, connected in series to form the converter arm. So each branch of such branch is called an arm of the converter, and the cell may have several different topologies, but the most common one is the half bridge, where we have two power switches, the top power switch and the bottom top power switch. And the voltage here is controlled by controlling the state of those switches. If the top power switch is conducting, the capacitor of the cell is connected to the terminal, so the capacitor voltage appears at the terminal. And on the other hand, if the bottom power switch is conducting, we have a short circuit here and we have 0 voltage at the terminal. And so as the cells are inserted or bypassed, so the capacitor is connected or bypassed, we have the total voltage of the arm as a result of the sum of the cells that are inserted. So we can see here the orange waveform and the yellow waveforms for the top and the bottom arms. The phase voltage that will appear here to the load will be half the difference between the top and the bottom voltage, giving rise to such a nice waveform as you can see here, the blue line. Those converters are controlled centrally with a unit I call here a center controller that tells the cells the state that they have to be. So if they have to be inserted, connected, or bypassed. And also an important thing that happens when a cell is inserted, so the top power switch is conducting, is that the current that is flowing through the arm is flowing through the capacitor. And if the current is positive, the capacitor is being charged. If the current is negative, the capacitor is being discharged. And as the number of cells that are inserted is changing over time, the cells might have their capacitor charged and discharged unequally, and this voltage may drift. So one important function of the central controller is to choose correctly which cells will be inserted at a certain time to make that this voltage, the capacitor voltage, stay in a certain band, safe band. And also, if the cell is bypassed, then the current is flowing only through this bottom power switch, and the capacitor voltage stays the same. Well, when it comes to the control diagram, I won't explain it in details. It's a way of controlling it. It's a cascaded control, so we have an inner loop where we control the currents of the converter, and the outer loop we may control the terminal magnitude. So in this example, the reactive power and the DC link voltage, we could, instead of the DC link voltage, the DC side voltage, control the active power that is flowing through the converter. And also, as I explained on the slide before, the capacitor balance is imperative to keep the converter operating. Another control objective of the central controller is to do the modulation. The modulation is the process of getting the reference, that is the output of the controller, and transforming it in the comment to the switches. So how many switches have to be inserted. And lastly, we have the circulate current that I want go into details here because they are less relevant to this presentation. Well, in the most simple or not really simple, but the most straightforward way of controlling the converter, we would have a central controller and physical connections from the central controller to each cell in what we can say a star topology. And I'm showing here single connections to the cells, but in fact those are more than one fiber optics or wire, because we have at least 2 power switches on each cell. You may want to get an error feedback from the cell, so in fact we have here at least 3 fiber optics. And as you can see, or infer from these diagrams, that the links are rather long. If you remember the size of the converter, it's the size of a building, the central controller is in another room. You can imagine how many, how long those connections end to be. Another advantage of this star topology is that the interface of the central controller has to be modified depending on the number of cells the converter has. And also it only carries on-off commands, so it does not give us support for auxiliary services. On the other hand, if we introduce digital communication, the first benefit, or the most obvious benefit is that we are able to change from to flexibilize the topology of how the central controller connects to the cells. I showed here in this example a ring network, but it could be different ones, as I will discuss later. In this case, we have simpler connections because the cells are connecting only to their neighbors. The connections are shorter. If we use digital communication, those links can be full duplex, what means that the data can flow in this direction, but also in the other direction. And we have the possibility of more functionality. So the cells can send data to the central controller. It can receive online parameterization. It can the cells can exchange data between them. So what gives rise to another control possibilities. We could, for instance, with the converter operating, upgrade the firmware of a given cell. So, as we introduce the digital communication in the internal control network of the device, we give rise to a network-controlled MMCs. We have then to consider several aspects. I discussed all those aspects in the thesis, though in this presentation I stay more focused on the last 3. But it's important to highlight that reliability is a key issue in such application domain. We are dealing with transmission of energy. We can't have the converter can't fail for single reasons. As I said before, the network topology is the most obvious benefit of introducing the a digital communication network. We could have several different topologies, so ring, tree. The star is not interesting, as I already discussed. The bus is also difficult if you consider the length that a bus would have. And we could also conceive a hybrid topology. If we consider the ring, then tree, the top ones here, well, the ring is the simplest topology to offer 2 alternative paths for data to flow, what gives us easy fault tolerance. and it minimizes the lengths between the cells because each node is connected only to the neighbors. But on the other hand, the performance greatly depends on the size of the network, because from data to go from one node to the next one, it has to pass all the nodes that are in between. And the tree, on the other hand, has better performance, especially when data is flowing from the root, so from the root here to the leaves, or between the leaves that are sharing the same switch. The connections are not as short as in the ring case, but anyway, if we remember the size of the converter, we are still able to reduce and simplify the connections of the deployment of the network. But the tolerance to fault is harder. If one switch fails, all the cells connected to it stops receiving information, so this is can be really an issue. It's important also to mention that the switch propagate errors, so if the packets being transmitted here get corrupted, the nodes that are after the switch will receive, all of them will receive wrong data, what's of course not desirable. And as we have more switches, we have more equipment that can fail, so there are reliability issues. In this presentation and in the literature, we always consider a ring as the most suitable solution. I also do it in my work, but it's very important to consider that the ring has performance issues. So I will use throughout this presentation the minimum cycle time as a figure of merit to compare different solutions. And I define it as the time between data updates in all nodes. And if we see here the equation of the MCT for a ring network, we have the n, in this case, is the number of nodes as a linear factor influencing the MCT, the minimum cycle time. The tree, on the other hand, as we may have different levels, we have a logarithmic behavior or count for the number of hops that a packet will pass, and then the performance is much better as the network size increases. I said when introducing the digital communication that it gave us the possibility to think in different control strategies. So in a centralized control, if we introduce the network, basically what we have is that instead of the directly commands to the switches, we have a network interface, the network and the data coming to the cells. But we can also think in migrating part of the functions to the cells. So in this case, I show the balancing and the modulation could go to the cells, what gives rise to a part of decentralized control. So most of the control is still run at the central controller, but some important functions are running here at the nodes. So after this introduction, let me tell you a bit what work we had. We don't have so much interest in the literature in this application, so I try to mention the most important ones from my point of view. So the first protocol proposed using high-speed communications for power electronics converters was PESNet. It appears in 1999, and many years passed when a new work tried to use a different protocol. It was work by To and Noron in 2013, that they verified that EtherCAT has enough bandwidth, speed to or performance, and could also be a proper solution for such types of convert. And they also demonstrate that it has a low synchronization error and jitter, and it is fault tolerant. Afterwards, in 2015, Karsten et al. Proposed the CycleBus. It's very similar to EtherCAT. It used the same principles, the summation frame and the on-the-fly processing. So I don't consider it too much a contribution, but anyway, it's work in this direction. And Tu and Ludwig compared the CycleBus with PESNet and found it to be faster than PESNet, although the comparison to EtherCAT is missing, so probably it's very, again, close to EtherCAT. Also, researchers from the Aalborg University implemented a partially distributed control, as I showed on the slide before, and the main purpose was to reduce the amount of data flowing on the network. I will also discuss it a bit more later. So, how is PESNet and what are the principles of it? It was proposed in 1999, as I explained. It's based on macro and FTDI. FTDI is a standard or a technology that was used for the fast Ethernet optical connections. So it's very similar to 100 bus FX fast Ethernet. It uses a master-slave module and it defines two frames. The first frame is addressed to a single node. It has a fixed length. It carries only 9 bytes of data for each slave, and the master sent 1 datagram for each slave in each cycle. And after it has set the data to all the nodes, it sends a synchronization frame that will make the synchronization of the frames and make the nodes to use the new data that has arrived. And the synchronization frame, it has a comment to signal that it's a synchronization frame, and the address of the cells of the nodes in reverse order, so that every node receives its address kind of simultaneously. To do it, it inserts new data between the addresses, and this is how the synchronization works. It ends being a very long frame that has to be passing over all the nodes at the same time. So the drawbacks of PESNet is that it has a low efficiency. The header is 3 bytes and the data is 9 bytes only. So we don't have a good ratio here. And the address is limited to only 8 bytes, 8 bits. So 31 slaves, 0 is reserved. It's not so interesting for this application where we have hundreds of nodes, but anyway, it's important to mention this protocol. PESNet is very well defined. You have a defined datagram, you send this data, you have the sync node, so the minimum cycle time is basically fixed. It depends on the number of nodes, and the delay between the nodes that will define how many new data you have on the synchronization frame. But in fact, you basically have fixed cycle time, depending on the size, the network size. So we have here for 30 nodes, as an example, about 50 microseconds of cycle The EtherCAT, which is the other protocol already used in this application domain, was introduced by Beckhoff in 2013. It's a popular industrial Ethernet protocol. It uses fast Ethernet, most often fast Ethernet, but also low voltage differential signals when you are inside the modules. And although you can connect the nodes in different ways, it always ends up being a logical line because the frame has to pass all the nodes in a given sequence, as this picture shows. And it uses two key technologies. So the summation frame, which means that one single frame carries data addressed to several nodes, and those nodes can read from the specific positions or write to those positions. And it has the on-the-fly processing, such that the node does not store the packet to process it and then send it to the next one, but as information is passing, it reads the data or writes to the positions where it has to write to. The drawbacks of EtherCAT, well, first it's unstandardized protocol, so we have limited flexibility. Also, it has special implementation of the slave nodes, so only a few companies supply these implementations, and we have to deal with them or live with what is provided. In this case, it uses fast Ethernet, and it will stay using fast Ethernet as long as Beckhoff decides not to migrate. And also, the node forwarding time is rather it's higher than 700 nanoseconds. So if we see the minimum cycle time, it's again dependent on the number of nodes, and it has not the limitation as before of addresses, so we can address many more nodes. But anyway, above 250 nodes, we are already have cycle times more than 200 microseconds, what I put here as a limit for a good control performance of the image. So this was a rather longer introduction to the theme, but somehow it's important to do it. And what was the objective of my work was to seek solutions in both the control and the network domains to allow the use of digital communication networks in MMCs that have a large number of cells. What is the most typical application? And for that, then we come to the contributions or to the real work. The first approach was to do a network and control co-design. The works I showed before, they picked one technology that was already established and then employed it, or designed a protocol such that it covered several different domains. So the PESNet was designed for power electronic converters, not for this converter specifically. In my case, I'm trying to design the protocol and pick our control strategies or develop control strategies that will make the performance when they are combined better. The first protocol proposed is the TT ring, time triggered ring. It again uses partly decentralized control to reduce the amount of data that has to be carried by the network. It has two phases: the cycle time, the cycle and the interslave phases, and a key characteristic is that it allows fast forwarding. So we reduce the forwarding delay of a node to a minimum to reduce the minimum cycle time. So I showed already a bit the partly decentralized control. In this case, we use a control strategy that uses data from the neighbors, so that we don't need to send measurements to the central controller. And the PWM is also executed locally at the cells. At the cells, yeah. And this is a time-triggered protocol where we have two phases. On the first phase, the cycle phase, the central controller disseminates set points and measurements that are necessary at the cells. So only one packet circulates the network. And on the next phase, the interslave phase, the cells share data with their neighbors only. So data is flowing in this direction, and this node sends data to this one and to this one, using fully utilizing the network, the bandwidth of the network. In the cycle time, as this protocol is time triggered, the nodes know a priori the type of packet that is coming, so it does not need to read any data inside it to know that it has to send the data forward to the next node. And because of that, we are able in the cycle phase to just get the data from the receiving port and connect it to the next port to transmit it to the next node. Doing so, we only lose one clock cycle here, and then we minimize the forwarding delay to only the latency of the PHY, that can be as low as 370 nanoseconds, plus one clock cycle. This is the equation of the MCT ring. Important to mention the dependency of the size of the network with the forwarding time, that in this case is minimized, and we have the benefit as we will see in the comparison. And we have two frames, because one for the cycle phase and the other for the interslave, so we have the overhead of the two packets and the data of the payload of the two packets. Because it's time triggered, we need a guard window, so we have also this time lost. That's it. So the key advantages of the TT ring: we have minimum forwarding delay at the cycle phase. We fully utilize the network bandwidth in the interslave phase. The payload is fixed because we don't have dependency on the number of nodes on the data that has to be sent, thanks to the interslave phase. And as we use a partly decentralized control, we have less computations at the central control. Yeah. The TT ring achieves very good performance, but it's limited to one specific modulation and sorting strategies. So we try to design or we investigated how we could use different modulations and sorting strategies, and this gave origin to the DieSortNet protocol. It also uses the IDRCAT on-the-fly processing and the summation frame, and we resort to three strategies to make it as fast as the TT ring strategy. Those are the dual insertion sorting, the distributed min-max identification, and the compact modulation strategy, as I will explain now. Well, the sorting strategy is on the original paper that introduced the MMC was the balancing strategy employed. It works as follows: the central controller, each cell has an identifier, and the central controller keeps the list of the cells in ascending order from the higher voltage to the lowest voltage. And it picks the cells with the high from the list according to the current polarity. So it chooses the cells with the lowest voltage if the current is charging the capacitors, or chooses the cells with the highest voltage if the current is discharging the capacitors, to keep the capacitor balanced. But this causes that every cycle the list has to be completely reordered, and the cells have to send their data to the central controller to be processed, causing a delay and a dependency on the number of nodes to the cycle time. The dual insertion strategy that we propose, it's different because at each cycle we still have the list, but only two cells are two positions are changed. So we identify one is the cell with the minimum voltage, which one is the cell with the maximum voltage. So in this example, 4 would be the cell with the maximum voltage, 7 the cell with the minimum voltage, and we move those cells to the top and to the bottom of the list. So to the top and to the bottom of the list, and the other elements are just moved to accommodate this change. So in this case, we only need two information: which cell has the minimum voltage, which cell has the maximum voltage, removing then the dependency on the number of nodes for the balancing of the capacitors. We did it we went beyond that, so we thought of distributed min-max identification. So the information has not to be transmitted to the central controller for this identification. It works as follows. The frame has a dedicated field where the maximum information is stored and to which cell this information belongs to. The central controller transmits this information with the minimum possible voltage here, and as the packet is passing the cell checks the information. If the voltage that's inside the frame is lower than the voltage that it has, it replaces the data and replaces also the index here. The same works for the minimum voltage, so at the end the frame comes back to the central controller already with the information of what is the maximum voltage, what's the minimum voltage, and to which cells they belong to. Using those two strategies, we don't need to transmit all the data to the central controller. We have the fixed payload for the sorting. So the next dependency we would have on the number of nodes is for the modulations. To reduce it to a mean, we propose a compact modulation, so we split the modulation in two parts. One part that is telling the cells only if it has to be on or off, so we need only one bit for each cell. And to make the control more, the resolution of the modulation better, we have a PWM part working like that. So we tell one cell that it will stay inserted by a certain amount, a certain dirt cycle, and we only need a few cells to really have a good modulation resolution using this strategy. So for the minimum cycle time, we still have the dependency of the size of the network. The sorting, we have only this dependency on the size of the network because of the address. How many bytes do we need? And for the PWM, we have a factor of 8 here. That is better than it was or works before. So to summarize the advantages, we have a low forwarding delay. The file delay plus 2 clock cycles would be the minimum. The payload is fixed for the balancing. We support the sorting algorithm family, so we have several modifications of the sorting algorithm that can be used. The modulation strategy is flexible. We could use several different strategies. And as we are distributing part of the processing to the network, we have also less computations at the single computer. So when we compare them, PESNet is only at the beginning here because it's limited to 31 nodes. EtherCAT is this dashed line here because it has a forwarding delay of 0.7 microseconds, and also the payload being influenced by the number of nodes. And the DSortNet and the TT ring are here. So at the end, much faster. So around 400 nodes, it's more than twice faster than EtherCAT. And this is a zoom for small networks, where we see that PESNet is not really interesting, only for small networks, and to give you an overview of a better view of how is it at small networks. So we can see that using this network code and control codesign, we can really accelerate the network. And for the ring topology, we can't be much faster than that. It's a limitation of the ring.
Tomás, I would suggest, just because it's getting too long, that,
yes.
that you just give a brief idea, because those are the two main contributions. Then you just give a brief idea of these ones.
Yeah, I forgot to say, but I knew that I would run out of time. I try to explain better this beginning because I think it's more interesting to the audience, and then I just pass. Well, I try to not only I wanted to reduce the latency, the end-to-end latency, because it is influencing the control performance. And when we talk about end-to-end latency, there are other factors that have to be considered. So on the master side, we are sampling the data and running the control algorithm. And about the net, when we have the digital communication, we have the master stack delay and the network interface card delay. And when the data gets to the slave, we have to get this data out of the network to the application software that it's running at the cell. So we didn't find much information on the delays inside the nodes in the literature. So I made several measurements using a Zinc device with different Mac media access control implementations. The results are here, and those marks are interesting because they are somehow representative of what we find in the semiconductor industry. And we see here again a dependency with the amount of data. So we proposed accelerator that the main challenge that this accelerator promotes is that it copies data that's being received directly to the end location where the software will use it. So we, doing that, we remove the dependency of the reception of data with the payload. This is the picture, the graph I showed before, and the green line here is the reception latency of the node using this accelerator that we propose, so we don't have a dependency of the number of data, amount of data. Well, I think this topic is less interesting here, so I will only say a few words. We might still have a delay that's too long for the control, so I propose to use let me just pass a model of the plant to compensate for the delay that the network introduces, and doing that we can improve. So this is without compensation. Here is with compensation. We can improve the control performance of the converter. And those results were taken using a prototype that we have in Alcala. It's in Alcala, yeah. And do you want to talk about the co-simulation, or you just
You can quickly give a...
Yeah, the co-simulation is important because the MMC are high voltage, high power converters that are in mission critical applications. So an accurate simulation is very important. And we have, when using digital communication, we have several domains. We have the network domain, we have the control domain, and we have the power circuit domain. So it's important to model those as good as we can. And for that, we use Simulink and Omnet. The typical co-simulation strategy, we have both simulators running lockstep, so they start at the same time, they run without communicating to a certain point, then they share data, they run again, they share data, but this makes the simulation long and time consuming for the and computational intensive. And what we propose is that in this application, in fact, the network, the control and the power domain are not influencing the network domain. So what we can do is we run the simulation domain, the network domain first. We produce data that is used as input on the control and power domain. And doing that, we separate both domains, and we can be much faster. This is an example of the Omnet simulation, and this is a result of the co-simulation. So when we have a leak loss probability, this is the way for the voltage generated. We see that if the link loss probability is higher, the voltage deviate more often from the reference, and the loss of packets degrades the control performance in terms of THD, rise time, and regulation of the voltage and so on. So it's important to consider the influence of the network into the power. Good. Then we come to the conclusions. Well, the codesign enables to push performance of the ring network to the limit. We can't be much faster than what the figures I showed. The TT ring has the best performance from the protocols I showed, though it's limited to a specific balancing strategy and modulation strategy. The DistortNet protocol is the first protocol to reach the cycle times really close to the minimum and still allow a flexible modulation strategy and the use of the sorting balancing. And the important aspects of it is that it distributes the balancing to the network and removes the dependency of the payload with the number of nodes. I just jumped, but we propose compensating the latency of the network to improve the control performance. And yeah, I'm not going into details here. And about the co-simulation, MMCs are expensive converters and accurate simulation is paramount. So a new simulation strategy was proposed. It's more efficient than the traditional co-simulation because we don't have to stop the simulation in runtime to exchange data, and we are able to do it because the communications influence the power control, but not the other way around. And the co-simulation result shows an impact of the network implementation on physical, let's say, magnitudes. Lastly, in my future works, I have to investigate the insertion sorting strategy further, because it's still limiting the number of nodes that the DSortNet protocol is able to support. I want to implement the tethering network and get experimental results. I want to validate the proposed protocols in a hardware-in-the-loop environment. So I designed a board to emulate the converter, and I will still work on that. The use of the ring network allows, in principle, to have fault tolerance, but it do not guarantee fault tolerance per se. So the protocols have to guarantee that, or to support that. And as I showed, the ring topology has limitations. So the next step would be to investigate different topologies, hybrid topologies, and all the implications that they come with them. And also work a bit further on the co-simulation strategy and compare it really with a traditional one to really check have to quantify the benefits. Okay?
Thank you.
Thank you very much for invitation.
I think we still have time for a couple of questions.
Please, some questions.
Anyone has anything to ask or any doubt, or if you fully understood? Ali.
Okay, I don't know much about this field, but just one question for curiosity. Why you cannot distribute the control and then just basically do the communication between the control system that are distributed?
You mean between the cells? Just
Yeah,
just
so
between
you
the
have
cells.
a controller for certain cells. I mean, it depends on perhaps on the dimension of how they are placed in that cell. So you have one controller for one rack and then another controller, and then you do the communication between the controller. Okay, this whole rack.
Somehow you could do like a hierarchical control, where you have controllers for controllers that are in a lower hierarchical level, controlling a few cells.
Exactly.
And others. You could think of something like that. And yeah, somehow you are migrating to a tree topology when you do that.
Okay.
You could think the controller as a switch or somehow switch. One manufacturer do, Alstom, GE has a patent in this sense, but we don't have it very much on the literature. But it is a possibility.
Because if you have separate controller for each of those, right, you can control those cells by this controller, and then basically you give the feedback to the main controller that, and this is just one wire instead of the wire from all the cells.
Yes.
So this way you can reduce the somehow, I don't know.
Yes. Yes, you could.
Know much about this.
But do you believe it has a negative impact somehow, or would you just gain from doing it, or is there a trade-off when you do that?
It's very much like the tree topology. So the problems with the tree topology we could foresee here. So we have more devices. Those devices have to be reliable. So we need to ensure fault tolerance. So if one controller fails, another one has to take the whole of this one because you can just lose all the cells that are connected to it. But I think it's something to investigate for sure. The ring is limited, and we have converters with 1200 cells, 2000 cells.
So is it the ring topology, is it scalable? For example, if you add more cells, can you do that?
Sorry?
Yeah, that's what you're saying.
But what if a cell
If
gets
you go to
damaged?
very large, then it's not scalable.
Sorry?
What if a cell gets damaged in the ring topology?
You still in the ring you have we have a ring here. As the data flows in this direction and in this direction, if one cell gets damaged or this link is broken, the data can arrive to here from this direction and can arrive for the other cells on the other direction. So if one cell is broken or a link is lost, you still are able to update or to talk with all the nodes.
But you seem to have said that you would reach the nodes almost instantaneously, right? So, if I understood well, it seems to be the case that the size of the ring has no impact on the analysis that you are conducting.
The size of the ring has impact because the data is passing the nodes, and as it passes the node, it suffers a delay. So as the number of nodes increases, and for the counter you need all the nodes to receive the data to really be able to apply this data to the switches, then you have at the end a longer delay, a longer latency.
So if you put some control networks in the middle to do this tree topology or something, you must have a trade-off about you increase the MTBF because maybe you have more problem because you have more equipment, but you probably decrease the time to communicate with the device. So in the regular work of when it's working, probably we don't know much about the subject, but probably you can communicate with the devices in a small time. So what is more important in this case? I think that you were saying that the time is most important, or the fault tolerance. Which one is most important in this case?
Well, the fault tolerance is let's say it's paramount. You need to have fault tolerance because you can't just lose 1000 megawatts because of a failure in a switch or in a link. But again, I developed the work on the ring network because I wanted to see how much what was the minimum cycle time able to reach with a ring network. But I agree, or I'm really willing to investigate other topologies, and because, as I showed, the ring network is limited. If you have 1000 nodes, you can't use a ring network, not with Ethernet. So you need to use it. You have to resort to a different topology.
So for example, why not using a network on chip, kind of a technology that is more scalable but may not be very efficient?
What do you mean a network function?
So basically you have all routers, and then you have the cell connected to that routers.
Yes, but how many routers would you need for a network of this kind?
You will need one, not all router, but
So
you need
you-
this communication for each of those cells maybe. Yeah.
So what you mean would be a hierarchical topology with routers. So
Yeah.
for switches, in this case it would be switches, that's what we were talking. But the problem with the switches is exactly what he said, is that the reliability is way lower because
Then you
each
need
switch controls the communication of a set of cells. So when you miss or when you lose a switch, you have a part of the network out. And that is a big deal. And in this case, the ring is the only topology that allows you to immediately recover from a link failure or a component failure with just working on the protocol, right? Without having to replicate components. So the tree topology always requires that you replicate switches in somehow, or you have different routes by having them connected in alternative paths, which will require rerouting on the fly. And this might be much more complicated than the kind of rerouting that you have to do in the ring. In the ring is just switching directions.
So,
and-
Let's do that.
and the ring of switches, is it possible?
Sorry?
The ring of switches.
Yeah,
So,
somehow it's,
It's a hybrid. It's there.
you have a, this is quite typical, right? And
Yeah.
so we have a ring of switches, and then, so if one, if one switch fails, you lose those cells.
Yeah.
But
Still you need redundancy in the switches
Yeah.
anyway, so that is always the issue.
So this maybe is basic question. So we're thinking to the physical. This is physical connection. Right? So this is a physical ring. It's not that the apps. It's not logical.
yes.
So the current deployments are star topologies. No? The existing deployments
Yes.
are star topology. So what if this ring topologies as thinking like a logical topology? So the protocol. So you have the deployment, which is a star, and you work with the logical protocols that are a ring. Is that applicable to that scenario?
Somehow the star deployment is what we want to avoid in the first place.
To what?
The star deployment of the net
You want
is what we want to avoid.
No,
So
but I am thinking that you have it. I don't know if, for example, in internet scale, there is like a ring, which is very famous, which is consistent hashing, which is hashing tables, which is a very huge ring base that use like jump for less hops in order to get like a better result. But this is very scalable, but a logical level. But the good is that you can use it in the existing deployment. So that's why it was key. So maybe star topologies you want to avoid, but the ring will not scale too much as a logical ring. Is that a good direction, you think?
I'm not sure. That's,
Logical always implies more delays because you are basically converting. And so, I mean, you can do a logical ring on top of, I don't know, something else, but then you don't have the physical property of the ring. You only have a logical property in the sense that you communicate only in one direction, and so you have only one, let's say, destination. And so you basically build the ring. But then you miss the property of the physical ring, which is actually what we're aiming at.
and also you will get congestion on the.
Yes, but the ring usually also give more latency.
The ring gives more latency. That's true in some sense. In this, that's what we saw here, because as it goes around, it has. So it's the benefit is not for free. So there's and that's exactly what Tomás was working was on the limitations of the ring. So to see how far could he go in reducing the the downside of the ring, while keeping the good side of the ring. So that's basically Tomás' contribution. That's from my point of view, if I said it correctly. So the limits of the ring.
Yes.
One last question.
So exactly. Before checking other topologies, I want to show what the ring is capable of. Somehow.
If you lose both the neighboring nodes, the whole network is gone.
Sorry? Again?
The ring is good if you just lose one node.
Of course.
If you lose both, neighboring one,
That's
the whole thing is gone.
But everything is
Yeah,
based
but
on-
most of the time we deal with single faults, right?
This is all based on the fact that the probability of two simultaneous faults is way, way lower than
You
1.
have time to fix
And
it.
so,
When it's bugging, you have time to fix it.
So the thing is, as soon as you have one failure, you immediately call the system is still working because of its fault tolerance mechanism, but you already call the team, the maintenance team, to fix the system.
So you hope that.
Or at least in-
Gets-
Yeah.
We call in reliability domain. This is called the redundancy attrition, which means that there's a period of time during which the redundancy is lower, and so or you miss. In this case, you completely miss the redundancy you have, right? And so you have to reduce that period of time to the minimum because you don't have protection. And so let's end. So I thank Tomás very much for presenting his work here, for sharing it with us. Thank you for coming and for the interaction. And maybe offline, if any of you are interested, we can have lunch together somewhere, grab a sandwich and discuss. Thank you very much.